In the overview section of surface integrals, we found that learned that there were two kinds of surface integrals, one being the surface integral of a scalar function, okay, through the part of the surface, okay, which is otherwise known as integrating over the UV parametrization of the surface, the vector field, the scalar function along the surface, and then the magnitude of RU cross RV du dv. And to make this work, to make this kind of integral work, we need to know what the function R of UV is called the surface parametrization. Okay? So that was one of the integrals we needed to do. The other integral we needed to do was the surface integral of the vector field, f dotted with n d sigma, otherwise known as the double integral of the vector field along the surface, dotted with the cross product of RU cross RV, and then need to do a du dv integral integrating over u and v. And again, we're seeing that we need R of u comma v to plug into the vector field and also to compute these first derivatives. Okay, so the key to getting started is simply parametrizing the surface, which is what is done in section 16.5. Okay, and what you're seeing on the screen here is just a screenshot from the textbook, and what I would like to do now is to kind of dig into a couple examples that we are prepared for from our prior understanding of cylindrical and spherical coordinates and such. So let's look at a couple examples. So you'll recall that we have looked at a transformation from R theta z space, and that transformation gives us something in the xyz plane, and that transformation was x was equal to r cosine theta, y was equal to r sine theta, and z was equal to z. And this is what we knew. R theta and z were what we knew as the cylindrical coordinates, and this is the cylindrical coordinates transform. Okay. So notice, for example, that if you fix any two of these variables, and let's just pick two at random. Let's say that you pick r is 3, leave theta alone, and pick z is equal to 0. Then what happens is you get x, something in the xyz plane. And what is that thing in the xyz plane? It is r is equal to 3. Theta, we didn't specify what it was, so it's left alone. R is equal to 3. Theta is left alone, but z we set to be equal to 0. And you'll notice here that there is a vector valued function. There's 1, 2, 3. It's a 3D vector valued function in one variable, and that one variable is theta. Which means that we have a 1D vector valued function in 3D, which is the equation of a circle of radius 3 that is sitting in the z is equal to 0 plane. Okay? So what we've just drawn there is just the outside of this circle. It is just the circular region, and the radius there is radius is equal to 3. Okay? But we can take a step back from that, and we can leave r and theta unspecified, and then you can set z equal to 2, for example. And now you're in the xyz plane, but what is it that we have? You have r cosine theta, r sine theta, and then c is equal to 2. Okay. And now you have a 3D vector valued function, because there are 1, 2, 3 entries, in 2 variables, and those 2 variables are r and theta. Okay. And if you think of those parameters, let them change according to whatever you wish. Like, for example, theta could go from 0 to, say, pi, and r could go from 0 up to, say, 4. Okay? Then what you have here is, in the xyz space, okay, you have, particularly the z is equal to 2, z is always equal to 2, so in the z is equal to 2 plane, something interesting is happening. We knew that r cosine theta, r sine theta described a region in polar coordinates. Right? And so what we are seeing here is that we have a circle of radius 4. Right? That's the maximum extent of the circle, but the minimum extent of the circle was you had a circle of radius 0. But the radius is getting bigger and bigger and bigger. It's extending outward, okay, these circles. And then theta only goes from 0 to pi. So what we have here is this 3D vector valued function in 2 variables is the part of the disk. Well, it's just half of a disk. Half of a disk of radius 4. Okay? So this leads us to the definition that was on the first page of the notes that we just did. Right? This object here. Right? That the book uses r of u comma v to indicate, okay, r of u comma v is equal to x being some function of u and v, y to be some function of u and v, and z is some function of u and v. Okay, where u goes from some number a up to, say, u is equal to some number b, and v goes from, say, some number c up to v is equal to some number d. Right? This will be some sort of part of a surface in 1, 2, 3 dimensions, right? And you know it's a surface because there are 2 parameters. Okay? So it's in 3D because of the 3 entries, and it's a surface because there are 2 parameters. Okay? And so, for example, okay, one could look at r of u comma v would be u comma v comma, say, u squared plus v squared, which is a fancy way of saying that x is equal to u, y is equal to v, and z is equal to u squared plus v squared, but u was equal to x and v was equal to y. So what we have described here is the parametric form of the paraboloid. C is equal to x squared plus y squared. Okay? We'll show some pictures in just a second how you can test these things. Okay? If you add a page below, let's look at another example. Okay? Let's look at r of u comma v is equal to u cosine v, u sine v, say u squared. Okay? And you say, well, what is this thing? Well, you know it's a surface. There are 2 parameters. It's a surface in 1, 2, 3 dimensional space. Right? But what sort of surface is it? Okay. Well, you'll notice that x is equal to u cosine of v, y is equal to u sine of v, okay, and z is equal to u squared. But u squared, right, is the same thing as x squared plus y squared, because squaring u cosine of v and u sine of v will give you u squared cosine squared of u plus sine squared of u to get u squared. So what we are seeing here again is that this is again the paraboloid. But it's the paraboloid in polar coordinates. Okay. So if we look at those two different surfaces, you would plot them in Mathematica. For those that are using Mathematica, you could use u comma v comma u squared plus v squared. And u goes from, say, -4 to 4, because basically u is equal to x and v is equal to y, so we're going to try to plot this surface, which is the paraboloid. We'll see a paraboloid show up here, and it will be drawn in terms of, I think it'll come up here. There you go. There's a paraboloid, but it's got these pointy ends on it, because when you look at this from the top, it's kind of hard to see there, but we get a bunch of square grids. This is supposed to look like a rectangle viewed exactly from the top. So it's the corners of that rectangle that are making it the paraboloid pointy. But if you go to the u times cosine of v, u times the sine of v, okay, and let the z entry be u squared, u is in the radius position, so if you let u go from 0 to, say, 4, for example, v is in the angle position in the trig functions, so v is an angle variable, so v would go from 0 to 2 pi. You will now get the paraboloid, right? But when you look at it from the top, you can see that we're getting kind of the circular shape. We're getting the radial grid because we have plotted that paraboloid in circular polar coordinates. Okay, so this frees us up. These parametric equations are really useful for describing surfaces. They can do things that are easy to draw, for example, right? So let's see, how about drawing a circle here in the say z is equal to 4 plane, and the circle here has a radius of 2, right? But the outside circle has a radius of 2, but you want to describe this disk, okay, which is the solid disk. So it's like a frisbee rather than like the hoop that's surrounding the frisbee. So what we want is to describe the whole disk, okay, and that's easily done in these coordinates using parametrizations, because you would say, well, it's a circle, but the z value is always 4. And u goes from 0 out to whatever the outer radius of this, the outer part was, I think it was 2. And v, which is the angle, goes from 0 to 2 pi. Okay? So if you take a look here, and then just now the z value doesn't change, but it's always equal to 4. And the radius variable goes from 0 to 2. We now have kind of the region we were looking at. It's a solid disk that is in the z=4 plane. Okay. So in fact, like example here, another example, try to get as many of these as possible. If you have z is equal to f of xy, any function of those variables, for example, let's say it's a cosine of xy. There's a function of two variables. Okay, and you want to parameterize that surface, write it in terms of r of uv. You know, you can always let x is equal to u, y is equal to v, and then wherever you see x, put u, and wherever you see y, put v. And so that's always legal. Okay, and this would be the parametric form, okay, of a surface z is equal to f of xy. Right, so x is equal to u, y is equal to v, and whatever function, you just put x in for u and y in for v. This is often called the Monge parametrization. Okay, and for example, it is basically taking your surface cosine of xy, but putting in x for u and y for v. Y is equal to v, x is equal to u, and we're plotting that surface as a vector valued function using, in a sense, rectangular coordinates for the u and v. Okay. So there is the surface cosine of xy, but described as a parametric surface. And again, you can see here that we are plotting over a rectangle. U went from, u is the x, u goes from -2 to 2, we can see here. And on the y-axis, the vertical axis here on the right, we can see v going from -2 to 2. Okay. But let's take a look here. What if I wanted to plot this function over like a circular region? I could have done u cosine of v. Y could have been u times the sine of v, and x would have been u times the cosine of v, y would have been u times the sine of v, and now we have to do the cosine of this quantity, and u is our radius variable, so we need to adjust whatever its parameters are. Let's say u goes from 0 to 2, and let's go all the way around. V is the angle variable, 0 to pi. And now we should see that same graph, but drawn over a circle that is of radius 2. Okay. If you wanted to enlarge that circle, we could have gone from a circle of radius 4. Okay. And over a larger circle, that surface does more oscillations. And if you wanted to let the angle variable go only from 0 to pi, you would get that same part of the surface, but only half of it. Right? Again, we're looking at now over half of a circle. Okay. So parametrization is a really powerful way to describe a surface. And so, you know, you can even express pretty simple things. For example, like a plane. Let's say you have a plane that you want to contain the vectors 1, 1, 1 and 3, 4, 2. What if you want to have a plane that contains these two vectors? I should not call them u and v. We've already got, let's call them vectors a and vectors b. Right? And you want to come up with the equation of this plane. Well, you can write r of u comma v would be u times the vector 1, 1, 1 plus v times the vector b, which is 3, 4, 2. And so you would get u plus 3v, u plus 4v, u plus 2v. And u and v here represent steps in, say, the u direction, and v represents steps in the v direction. Okay. So let's take a look at this plot here. Okay. So we'll have u plus 3v and u plus 4v and u plus 2v. So we're getting rid of the crazy cosine function, which makes this thing really oscillate, and we'll do u plus, what was it, 2v? And let's say you want to take one step in that vector direction A and one step in the vector direction B. And here is the plane that's created. Okay. So one edge of it is the vector A, and one of the other edge is the vector B, and we've taken one step in the one direction and one step in the other and filled everything else in between. Okay. If you wanted to take 3 steps in the u direction, right, the plane gets wider in that particular direction, 3 times wider. Let's make it 10. The plane got, maybe we have a scaling problem here. Okay. And maybe you want to make it half as long in the other direction so that this thing, right. But at the end of the day, you're still getting the equation of a plane. You're just getting the plane that contains the vectors A and B. Okay, so that's a good introduction to some of the basic surfaces that can be parametrized. We'll do in one video maybe a couple more complicated examples than the ones we've just done here, but this is a good introduction.